Welcome for today's session. In this session, we are going to design a switch mode power converter. Basically, a switch mode power converter is going to be used in your PCs and for charging your laptops and charge controllers. So we need a constant output. For that, we are going to be using SMPS. So let us start to design a switch mode power converter. So first, I am going to be using a switch is here MOSFET. So I am searching the MOSFET in the library. As I got a MOSFET, so here I'm going to be remove that measurement port. So for this, double click on this your MOSFET, and simply you can uncheck your show measurement port and apply it. You can see here the measurement port has been disabled. So for this switch mode power converter, basically I'm going to be using a logic is going buck boost converters that I'm going to be used here. So for that, for a buck converter, one switch and diode will be there, and similarly for a boost converter also another switches will be there. So for that, I have been taken a two switches. So two MOSFET switch I have been taken here, and then I'm going to be using diode. So oh my god, I have been entered that sim cap diode, so I have to remove those sim cap diode because I don't need a sim cap. So we need a diode which is going to be used in power system. Okay, so let us search in the library a diode. I think we can search in the library itself. Yeah. Okay, here also you can search diode. Fine. So where it is diode? Yeah, it is presented here. So simply you can add this diode into your workspace, which is added here. So here also you can remove your measurement port of your diode. So I don't need a measurement port. So you can copy this diode and you can rotate this diode also here. Okay, fine. Yes. And then according to the buck boost converter, an inductor and capacitors will be present. For that, I am going to be choosing series RLC branches. So series RLC branch. So for an inductor, which is going to be one series branches I need, and for capacitor and another one for resistor load. So changes it into an inductor and then change this to an capacitor. Simply rotate it and change this into a resistor and rotate it. Yeah, now it is, everything is okay. So these are the basic components which is going to be presented in our SMPS. First of all, we need an DS supply. So I'm going to be using DC voltage source. Okay, so I'm going to be using a DC voltage source. So now I am giving a connection from the positive terminal of your DC voltage source, which is going to be given to your MOSFET, and the MOSFET output which is going to be given to your inductance, and the inductance output is directly given to your diode, and output of your diode is directly connected to your load. The negative terminal of your source also is going to be connected to your load. So in between a diode and MOSFET which is going to be presented here. So this diode is going to be connected after this switch. So between the source and another MOSFET, the diode which is going to be connected here, and the second MOSFET switch is going to be connected after your inductance. So the drain terminal of your inductance, which is going to be connected to the positive terminal, and the source is connected to the negative terminal. For our filtering purpose, we are using a capacitance at a parallel of your output. Yes. So this is a simple buck boost converter circuit diagram, and here we are using a 2 MOSFET switch. So for that we need to give a triggering pulse. To generate a triggering pulse, I am going to be using a PWM techniques. So in the previous session we have been designed our own PWM pulse generation. So here for our simplification, I am going to be using a direct PWM, which is going to be present in our library itself. Just you can type in your library, you can search PWM generator. So a lot of PWM generator which have been presented there. So here I am going to be using a DC to DC PWM generator that I am going to be taken here. So because we are converting in a we are regulating your output voltage in a DC formations. So for that I'm using a PWM which is present in a DC to DC converters. That is a PWM generator. So the pulse PWM generator, the pulse width output of your PWM generator, which is going to be given to your MOSFET switch number 1, and then the switch 2 also it should be get an PWM generation output signal. So for that I am going to be use the same generator what we have used in the previous session. The same, we are going to be invert this output voltage and we are going to be given to the second switch. For that what we have been used in the last session of your PWM generator, we have been used in logical operator. So simply you can type in a logical operator which will be presented in AND. So change this logical operator into an NOT gate. Okay, convert this AND gate into a NOT gate. Okay, so I have been converted right now here. So now, so output of your pulse generator which is going to be given as the MOSFET switch number 1, and similarly the same output which is going to be inverted and given to the switch 2. Okay, then to identify these two kind of pulse, I am going to be use a scope. So in the scope I can able to be measure these two kind of pulses. So I'm going to be measure the pulse of the two inverted and a non-inverted pulse which have been generated from the PWM generator. So in the scope I need two separate axes that I am going to be use. So number of input is 2 and change it into layout also, and you can go to that display, so legend. Okay, fine, yeah, very good, which have been, so here in that layout, two layouts that have been selected. Yeah, so now you can connect this. So what happened, let us see. Yeah, so two input. Okay, yeah, two axes which have been presented right now. So in the first port we can connect from that PWM generated output. Okay, so this is that is the gate pulse to that first switch which is going to be seen in your first port, and the gate pulse to the second switch which is going to be seen in your second port. Fine, yes, very good. And your output voltage across your load also we can able to be measure. This is to measure an output voltage. Simply we are going to be using a voltage measurement. That is, we can use voltage measurement. Yeah, so we can directly use an voltage measurement. So output of the voltage measurement which is going to be directly connected to that scope. So only one measurement that we are going to be connect here. So simply you can connect only one port. So in this part, So positive terminal and negative terminal which is going to be connected across your load, resistor load. So here you can able to be see your output across your resistor. So this is your overall circuit diagram which is going to be presented in your boost converters. So now it is an open circuit. So that means if you are giving any kind of parameters as an input to this load means, so for example if you are giving 100 DC voltage means, so there will be an variations will be there in your output according to your conversion which have been made in your converters. So if we need an exact output according to your load condition, so we need to give an feedback which should be taken from this output and it should be given to as an input. So that is going to be called as a closed loop. So for that also we can design the same thing. For to get a constant output in your across your load, I am going to be take a part of output signal and then I'm going to be given to an input of your source. So let us start to design that kind of thing also. So for that I'm using a gain. Okay, so I need two kind of gain that I need. So simply I can copy this. Okay, fine. So now rotate this gain value and I'm going to be use our reference signals, and based upon your reference signals you can able to be get a constant output at across your load. So for that I'm going to be using sum. Okay, that is to add the two output signal, I'm going to be use this sum port. Okay, that means I'm going to be add your output which is going to be presented across your load, which is going to be add with your constant value. So that is your reference value which is going to be add with your reference value. So you may give in any kind of reference value based upon your requirement. So I need an 50 voltage across your resistor. I need a 20 voltage across the load. I need a 40 voltage across the load. So depend upon our requirement we can able to be design the values, and here we can choose an reference value based upon our output signal which have been generated. So here which is going to be coming. So both the signal which is going to be combined together and it should going to be provide an error signal. Okay, so that error signal which is going to be given to an PID controller. Here I'm going to be use an PID controller. So you know very well about an PID controller, control system itself. We studied clearly about an PID controller. Simply this control also we can search is in the library itself, PID controller which is there. So rotate it simply, and output of the PID controller which is given to an saturation signal. Okay, you can rotate this also. Yeah, fine. So now you can give the error signal to an PID controller, and output is given to a saturated and again to the gain. So now here I need a sample pulse signal should be given to this PWM generator. For that I am using an pulse generator. So that is my sample signal should be given to a PWM generator according to here. And another one is I need to compare this output signal also. For that I am going to be use an relational operator here. Relational operator. So you can rotate this relational operator. Yeah, it is fine right now. So that is your first input is going to be in a pulse generator, and second input is going to be your feedback signal, and a combination of those things which is going to be given to an PWM generator. So now your circuit have been completed. So this is going to be an closed loop formation of your buck boost converters. So now we can give, according to our designing network, we can give an values for each and everything. So now I'm going to be change the values which is presented in our pulse. So based upon our requirement, I'm going to be given values here. So the amplitude is going to be 1 and the time period signal is going to be 0.0001 second. Okay, I think so far I have wrongly typed 0.001 second, and the pulse width is going to be the same, 5 phase delay is 0. Okay, then go for this relational operator. So double click the relational operator, it is presented in less than or greater than, so changes into a greater than or equal to. And then PWM generator, it is open the PWM generator blocks. The frequency which is presented is a 5000 frequency, changes into a 10,000 frequency. Okay, the sampling time is 0. And this is a not signal which have been changed there, and your inputs. So already it is presented in 100. So for our simplification, we can give a small kind of voltage. I'm going to be given 48. Okay, or 48 or 50 also we can give. Okay, I'm using here. So this is your parameters is going to be given. Input voltage is going to be chosen according to our values only. Any kind of input voltage we can give. Based upon the input voltage, we need to check how the output have been bucked or not. Like that, we need to check whether you are getting a constant voltage or not. So for that, we need to concentrate on this designing parameters networks. Let us check the MOSFET switch. The internal resistance is 0.1 ohm resistor, and the internal resistance which is present in the diode is 0.01, and snubber resistance also, which have been same. Snubber capacitance is infinitive. Okay, fine, no need to change these parameters, everything is in standard formation. And let us check the diode values also. Internal resistance is 0.001, very good. And then snubber capacitance also, yeah, it is fine right now, no need to change any values of an MOSFET and diode switches. And we need to change the values of your inductance, because inductance capacitance is going to be a major component which is a buck boost converter. Based upon those things only we can able to be deliver an required outputs. So here I'm going to be using 0.1 millisecond. Okay, 0.01 e minus 3. I'll apply it. Okay, and then the capacitance value I'm going to be use here. The capacitance value is 2200 microfarad. Okay, apply it. Okay, and your load value, I'm going to be using a resistor load, that is 100 ohms, that I'm going to be use here. So here we have given a gain value is 1. No need to change. The constant value is 26. The PID, the parameters which is presented in the PID is detailed parameters will be presented, so no need to change anything which is already inbuilt things. So and is saturated also. So we need given as a saturation time is -5 to +5, that is a saturation time which is presented. So here enable the zero crossing detectant, and you can uncheck your as a gain. When compared to your gain values, you can uncheck those things and apply it and put OK. And the gain value which is also presented here is 1. Okay, fine. So now save this model in the name of your experiment. I'm going to be save this model in the name of save as SMPC. Okay, switch mode power converter in the name of model. Okay, so one main thing that we need to insert in this circuit diagram, so that is an power guide. So that only one thing that we need to insert. After that we can start to run this model diagram. Let us check how this output is going to be present based upon your input. I'm going to insert here as a power guy. Okay, so we have inserted the power guy. Let us start the simulation. As it is compiling, it's checking each and every blocks, evaluating which have been completed. As it's right now, it start to running the MATLAB model. As you can see here, let us check in that output of your scope. Yes, you can see gradually the voltage which have been increased from 0 to the maximum range. Let us try to finish how it is presented. Let us check. After finally the model have been completed, and you can let us see the pulse which have been generated to that MOSFET 1 and MOSFET switch, that is switch 1 and switch 2. Let us try to zoom those things. So yeah, yes, you can see here after finishing, I think so far we can see in exact manner. Yeah, the pulses which are going to be generated here, you can see here number of pulses which have been generated using your PWM generator. You can see at the duration of your maximum time period in your P1 switches which is get generated, and here which have been presented in that inverted mode. So you can see basically this is the second pulse which is going to be given to the switch number 2, and this is your pulse which is given to your switch number 1. The combinations of your gate pulse. Yeah, so it is compiling right now. Only 15% is need to complete. After that we can check the output voltage, how we have been get, whether it is constant voltage that we have been get or not. We will check it. Yeah, so let us check your output voltage here. Yeah, and now you can see here you have been mostly getting a nearly 25 point something the value which have been get here, 25.5, 25.1, like that the voltage that you have been get at a constant values. So gradually the voltage which have been increased and the constant voltage that you have been maintained here nearly upon your 25 values. Okay, based upon your reference value that you have been maintained your voltage values which have been output of your load. So now we have came to the conclusion. So according to your input voltage is going to be 48 that you have been given, but in your output that we have been get nearly an 26 voltage, that is the voltage have been maintained at your load side. So for that only we have been taken as an closed loop circuits. So your output voltage across this capacitor is going to be nearly a constant voltage that you have been get. We can able to be given to you each and every parameters that we need to connect, whether you can use in a charger, either you can use it in PCs, everything that we can use based upon this SMPS. Okay, thank you.